Must have a flat battery. Better chuck it on the charger. No LED. This could be a job for MiracleMAX. Hey guys, welcome to MiracleMAX. As you've seen already, I've been given this cordless drill and it's got a flat battery. Now, how do I know that the charger is to blame? Well, for a start, when I turn it on, as you can see already, there's no LED. But how do I know that that's faulty? I'll show you. As you can see, this is a 12 volt battery charger. I happen to have also a 12 volt charger here, as you can see. And what happens when I plug this in? I get myself a little LED. So, what's causing the problem? We've already established that this is a 12 volt DC charger. But note what happens when I turn it on. So I've got my multimeter set up here and I get absolutely nothing. One of the major problems with these chargers, of course, is that they're actually glued all the way around. So you'll have to somehow cut it open. I'm going to use a Stanley knife very carefully. Another way you could use is a hacksaw. I may finish that off tomorrow, but it needs to be separated because they're glued together. Then we can have a look inside. And there we have it. Oh, it's only a linear. Very basic setup. As you can see here, we have what's called a bridge rectifier, which turns it from the AC into the DC that is used to charge our battery pack. Fingers crossed that we've just blown a diode or two. That's what I hope that it is, but it's also possible that we've burnt out some wiring in our power supply here, but we'll do some measurement and see what we find. The correct way to check diodes is by putting it on the diode setting on our multimeter here, and usually you've got to press this button as well to bring on our diode symbol here. Now, diode is like a one-way valve, so when we test it we should have a reading only one way. So if we check that, there's no reading that way, but if we turn our leads around the opposite direction, we should have probably about 0.5, I'd imagine, of a volt going through. There you go. It runs about 3 volts through it, and then it gives us a reading as to whether it's open or closed. So that's open there, and that's closed there, open there. That's open there. Hang on a sec. Have I got an open one? No, I haven't. There we go. Just poor contact. That one there. Close there. And open there. So at this point it doesn't look good for the little transformer. I'd say that it's got a broken wire in here, but I'll pull it apart and check it further. But as you can see, it's just a very basic transformer. It'd be what's called a step down transformer, where it goes from 240 volts into our 12 volts that we need. Ours is known as a step down transformer, which means that we get less voltage out of it compared to the amount of voltage that we put into it. So how does a transformer work? I'm glad you asked. In this particular case, we have two sections, the primary and the secondary. On the primary side, here in Australia, we would put in 240 volts through a series of turns, maybe 200 turns, going around a soft iron core. The secondary side may have as little as 10 turns, and we get 12 volts out of it. So that's basically how a transformer works in basic terms. So the diode pack appears to be okay. So my next step in the diagnostic process would be to check my transformer windings. Primary section is this one here that comes from our 240 volts. Just keep in mind that it's simply a loop of wire around a laminated core. So there should be continuity between this point and this point, shouldn't there? And this is the part that goes into the power point. So we need to put that on our ohm rating there, as you can see. And then we just check this and this. As you can see, there's no continuity there. So that tells me that there must be a break in the primary winding through here. The way that we can check the secondary winding, which is the layer of winding here, this black winding down here is covered in black tape, I should say. The primary section is up here, and that's wrapped up in red tape, just like a government department really. So to check our secondary winding, we need to check before it gets to our diode pack here, this point here and this point here. This is the two wires that come off our secondary. So we should have continuity there. So let's test that, which it does. It's got 4.3 ohms, which is fairly consistent with, whoops, just lost my contact there. 4.2 ohms, which is fairly consistent with what you would expect for a step down transformer. So the problem with this is that we have a break in our primary winding here. I'll just investigate further. If not, she's a throwaway item. According to the test that we've done, there must be a break in the primary winding, which is this one here that goes around and around this iron core and comes out here again. So what I'm going to do now, I believe that the whole thing has had it, but I'm just going to cut this off here just in case the solder connected to the primary is broken away. So I'll check that next. As you can see here, it's got a little thermal cutout, so that's quite possibly what the fault is, rather than, well, it does create a break. It's like a little fuse within the circuit itself. So what I'll check now is, okay, so there's the transformer wire. I don't know if you can see it or not. It's very, very fine. It's that little wire just there. And of course, then this second primary wire here comes from the AC, goes through this little thermal section here into the main wiring. So what I can do is just bypass that by testing it here and also here, because I know that's okay. That'll tell me if that little thermal cutout is faulty or not. So I've connected my negative terminal off my multimeter up here, and as you can see, I've got good contact there. So now if I bypass my thermal switch by going down to this point here, notice I've got continuity now. So that tells me, of course it's a high continuity because it's going through the entire primary winding of the coil of the transformer, but that's okay. It's got continuity. So that tells me now that the thermal switch is faulty. So all I have to do is replace that little thermal switch and the thing should be up and running again. So you can see the little thermal fuse there. It's rated at 130 degrees Celsius and 2 amps current. Now I've been able to find something that has the same sort of specifications, a little different in design, but it'll do the trick. This is the ones that I'll replace it with. As you can see, they're a little different in design, but they will do the trick. So now it's just a matter of soldering one into place and hopefully the unit will work. Not sure if you can see it or not, but one of the main primary wires has actually broken. You can see how tiny it is, and I'm going to attempt to solder that back on to the main input wire. It's not necessarily pretty, but after some testing it should be okay, I hope. The thermal fuse is actually this section here that's in some heat shrink. Because I had to solder it this way, the two wires would have touched, so I have to be very careful about that. So the other wire is hidden way back in there, and the thermal fuse comes in here and goes back to that wire. So there's the little thermal fuse that I had to replace. It was a bit painful to do, but I've come up with that configuration now, and I've got it all covered and insulated well. So really all I need to do is check for continuity before I power it up, and obviously the best way of doing that, as you can see, is I've just got my test leads on it, and I'll now come over to my multimeter and I'll put it onto ohms, and we should have some sort of reading there, which we do. We have 0.4, what are we after? 0.4 of a kilo ohm. So that's good. It's got continuity, so that means that when I power it up, I've checked my diodes, they're okay. Once I power it up, I should get my 12 volts DC power supply. Just before I pop the back on, I just want to check it and make sure that I'm getting my DC power supply out. So we'll turn him on, and I've got my multimeter connected there, and we are getting 18 volts. Now I know that appears to be high, but this is unregulated. It's just a straight linear one. So when we put the load on it, it should come down to the 12 volts. So we'll check that when we put it on the charger. What I've done now, just to check my regulated voltage, is I've stuck some wires inside the charger and hooked that up to my multimeter. You can see the positive one there, and of course the negative one in the back that I've put in. So what we need to do now is turn it on and check out our regulated voltage. We saw that we had 18 volts there before. That's miles too high for the battery pack, but like I said, that's not with an actual load on it. So now that the charger is hooked up to the battery pack, let's have a look and see. As you can see, the battery voltage is dropping down as we speak, but let's see what happens when we actually turn on the charger. And we're getting about 10.7, 10.8. Now remember, it's a 12 volt charger, DC, and you can see our little LED is on there. Now I believe that's a bidirectional LED, so it's red at the moment, and I think when it's charged it should turn green. I'll put it on charge overnight and see how we go. There you go, fully charged. We have a little green light there, little green LED, which is an indication of a fully charged battery. If we go over to our multimeter, we've got 12.81 volts, which is excellent. It's a fix and a complex issue made simple. I hope that you've enjoyed learning about the linear transformer, the operation and repair on our little power supply for our drill battery pack. If you've enjoyed this video, make sure that you subscribe if you haven't already. It's that little red button just there. And don't forget to give it a like and comment below. In the meantime, thanks very much for watching, and we'll catch you next time. Bye.